Good morning, dear students. Today we will start with our lecture with the discussion of Maxwell equations. Maxwell equations, all of us know that there are four Maxwell equations. Already we know that the first Maxwell equation is derived from Gauss law of electrostatics. The integral form of Gauss law of electrostatics says that the flux, which is E dot ds around the closed surface, will be equal to 1 by epsilon naught times of the charge enclosed. That is given by this. So this is the integral form of the first Maxwell equation. When we see the differential form, which comes out to be del dot E is equal to rho by epsilon naught. If we see the physical significance of this equation, basically the left hand side governs the divergence of electric field. Divergence of electric field, as you all know, that if from any point the field is outward, divergence will be positive, and if at any point the field is inward, the divergence will be negative. So based on the factor that the left hand side represents the divergence of the electric field, right hand side charge density nature can be determined. So charge density can be positive or negative, or we can say the charge is a scalar quantity over here. So that's the main physical significance over here, that we can determine the nature of the charge based on the divergence of electric field. The second Maxwell equation is derived from Gauss law of magnetism. For which the integral form says that the magnetic flux B dot ds is 0. And if we say the differential form of this, it comes out to be del dot B is equal to 0. Now coming to the physical significance of this equation, we can see the divergence of the magnetic field is 0. Divergence, when we see over here, in case of electric field, it is outward or inward. This can be a source or a sink. But in terms of the magnetic field, when we say, we have to have the north pole and south pole for a magnet. And if we see the magnetic field lines moving from one place to another, so the same field line is coming back. So making a closed curve. So if at any point of time, if we have a cross section area, so through that cross section area, the net flux will be 0. The field lines moving in this direction will be equal to the field lines coming back. So that says that in terms of magnetic field, we cannot have monopoles. So the physical significance is that a monopole does not exist. Third equation, which is derived from Faraday law of electromagnetic induction, it says that integral form of this law is basically the line integral of electric field around any closed curve is equal to the rate of change of magnetic flux density. Around any closed curve. And if we see the differential form, it comes out to be del cross E is equal to minus del B by del T. If we see the physical significance of this equation again, it says that time varying magnetic field produces equivalent electric field, and basically it's a time dependent equation. And it shows that time varying magnetic field produces electric field. So this need to be understood properly. The fourth Maxwell equation is basically modified Ampere circuited law, or we can say Maxwell Ampere circuited law. The integral form of that, like line integral of the magnetic field around an enclosed curve, is equal to mu naught times of conduction current density and displacement current density. Now over here we need to clarify the fact and the value of this displacement current density. So for this we have to have, like, if we see the equation given by the Ampere circuited law, which says that line integral will be equal to mu naught times of I, and then Maxwell modified it like where IC is the conduction current and ID is the displacement current, where ID is basically proportional to the rate of change of electric flux, and the value of this displacement current comes out to be epsilon naught d by dt electric flux. We all know that the total electric flux, if we calculate for a parallel plate capacitor in between the space of those two parallel plates, it comes out to be and if we make this a scalar values, number only comes out and if we take this in, which is actually displacement vector, and if we divide this A, we take this A into left hand side, it comes out to be displacement current density, which will be equal to this. So this is the total part, but when we talk about the integral part and the value where we are using like for this. So we can put the value in terms of current densities. So we can easily write IC in terms of conduction current density, and ID in terms of displacement current density. And if we take this will be so if then we use Stokes theorem, then we can easily get the value. First we will write it completely, and the JD value will replace from this equation this part. Okay, so this will be the complete integral form of Maxwell fourth equation. But if we find the differential form, we can easily find out using Stokes theorem, and it comes out to be del cross B is equal to mu naught times of conduction current density plus this value. If you see the physical significance, we can easily make out that this equation is time dependent, as well as we see that the rate change of electric field or we can say time varying electric field produces magnetic field. So this need to be understood in a proper manner, that where in third Maxwell equation time varying magnetic field is producing equivalent electric field, but in Maxwell fourth equation time varying electric field is producing equivalent magnetic field. So these things need to be understood in a proper manner. Now when we say that Maxwell equation help us to get the value of the energy or the energy associated in a particular medium, and we can actually calculate the flow of electromagnetic energy in a particular medium. So we can have the solution of this Maxwell equation, as well as the values related to the electromagnetic energy and flow of electromagnetic energy, or the value of electromagnetic energy density in a space. Then we need to solve these equations for different mediums. So our next topic will be solution of Maxwell equations. Now first of all, we are taking solution of Maxwell equations for free space. And the free space is charge free. So when we say this charge free, then there are certain parameters we need to consider, the values of different parameters for Maxwell equations. So first we will see how the Maxwell equation will change according to this environment. So first we will write original Maxwell equations in differential forms. So if we say that okay, there are 4 Maxwell equations, so we will write these 4 equations in differential form. The first of all is this one. So we can write it in terms of displacement vector also. Second Maxwell equation is this. We can write in terms of magnetic field intensity. Third Maxwell equation and the fourth Maxwell equation So in terms of H, we can write this equation as del cross H, because we can move this part here, Gc plus del d by del t. But the environment says that it's a free space, charge free space. So for the free space there will not be any charge. So we can write over here for free space charge density is 0. So as soon as this becomes 0 and our conduction current density becomes 0, because conductivity is 0. So Maxwell equations become, like you can say, a different form, and this can be written like A, B, C and D, like first, second, third, fourth. So the first equation from here, it can be written like del dot D is equal to 0. The second equation will remain same. The third equation will be same. But the fourth equation will be only this part. So if we see these 4 equations A, B, C and D, and there is a, you can say, a clear picture about the environment, which says that the charge density is not available over here. So now if we take the to find the solution, we take curl of C. So curl of C means this equation need to be curled. We have to take the curl of equation C. So that will be del cross E is equal to this. Remove this inside and it will be del by del T. This one. So we see that it's a curl of magnetic flux density B. And over here in the fourth equation, in the D equation, we can easily make out the value of del cross B. So we can put this value from here. But first then the left hand side, which is this one, we can get this solution as del dot E minus del 2 E is equal to now here del dot E is the divergence of electric field as the curl of magnetic flux density. So all these values we can see that over here we are available with the equation A and equation D. Equation A and equation D. So we'll use these two equations here. So using equations A and D. So we'll put the value of del dot E, which is available here, as 0. And put the value of del cross B from here. So over here it is H B by mu naught. So it will be mu naught del by del T epsilon naught E. So minus del 2E is equal to minus del by del T mu naught epsilon naught del E by del T. So this is the value we got over here. Negative sign will be cancelled out and this differentiation will go inside. So the value will be del 2E is equal to mu naught epsilon naught del 2E by del T square. So this is the first equation in terms of electric field we got. You can say like A equation. When we compare this equation with the wave equation, the general wave equation, we can get the value of the velocity of electromagnetic wave. But again we have to solve it for magnetic field also. So for that the same procedure will apply. Like for this part we have taken the curl of E. Then for getting the value, getting this equation in terms of magnetic field, we need to take the curl of equation D here. So in the same manner we will get del 2H is equal to mu naught epsilon naught del 2H by del T square. The second equation we got. So if we compare with general equation, general wave equation. What is the general wave equation? The general wave equation says that if any wave function psi is there, so for that wave function del 2 psi is equal to 1 by v square. This equation is justified. So if we compare this with any of the equation A or B, we can find that v square is actually 1 by mu naught epsilon naught, or v is equal to 1 by under root mu naught epsilon naught. If we put the value of mu naught as 4 pi into 10 to the power minus 7 and the value of epsilon naught 8.854 into 10 to the power minus 12, we can easily calculate the value of velocity as 2.998 into 10 to the power 8, which is very nearly equal to the velocity of light, or we can say the speed of light. So this value is velocity of electromagnetic wave, and it is nearly equal to a speed of light. So it clearly says that electromagnetic wave can propagate with a speed of light. Now, based on this factor, you can easily prove that electromagnetic wave, or you can say a light wave, is an electromagnetic wave. So in our next topic, we'll solve Maxwell equations for a charge-free conducting medium. That we'll take in our next class. So we'll solve. We can get the solution of Maxwell equation for charge-free conducting medium. That we'll take in our next class. Okay, thank you. Bye.